Hi everyone, welcome to part 2 of our video lectures on section 3.3 dealing with the derivatives of polynomials and exponential functions. In the previous recording, we learned a couple of derivative rules. We saw that the derivative of a constant is just 0, the derivative of x is equals to 1, and the derivative of a variable raised to a power is just given by the power rule. Now, in this video, we're going to learn a couple more rules that will facilitate the process of finding a derivative quite a bit. So let's go ahead and begin by taking a look at the derivative of a constant times a function. So let's say that we're given a constant c and a function f. That's a differentiable function. Then the derivative with respect to x of a constant c times a function f is given by c times the derivative of that function. So notice here that basically what's happening here is that you're taking the constant outside of the derivative and then just multiply it by whatever you get as a derivative. Very similar to the limit rules. So let's take a look at a couple of examples here. So I want to differentiate the following. And let's go for the first one and the last one here. Okay, so for the first function, we're given that f of x is equals to 5 times x to the fourth. All right, so taking the derivative then, we're going to get f prime of x is equals to the derivative with respect to x of 5 times x to the fourth. And since we have the 5 as a constant, then I'm going to go ahead and write it outside of the derivative operation. And then we're just going to get 5 times the derivative of x to the fourth. And here is where the power rule is going to come into play. So let's see. Since we took the constant outside of the derivative operation, we'll just take 5 times. And what is the derivative of x to the fourth? Well, we'll bring down the power and take away 1 from the power of x. So we should be left with a 4x cubed. Okay, now simplifying this one here a little bit. Now we just have 5 times 4, which just gave us a 20. So our derivative, f prime of x, is going to be equals to 20x cubed. And that's it. You found the derivative here. Nice and easy. Much better than using the limit definition here. Alrighty, now let's go ahead and take a look at the last function here, where we're given h of x is equals to 1 over 5x squared. Now this one here can be a little bit trickier because, well, for starters, we have a fraction, so that means that we need to rewrite it so that the x is in the numerator, not in the denominator. So this is the way that I like to interpret the problems. If we have h of x is equals to 1 over 5x squared, I'll reinterpret it like this. H of x is equals to a 1/5 times a 1 over x squared. This is the exact same thing, but now that you've rewritten it here as a product of 1/5 times 1 over x squared, well, we get to see here that we indeed have a constant here, and it's 1/5. Okay, so now we know that the power rule is going to come into play, and at the end, we're just going to go ahead and multiply by a 1/5. Now, in order to use the power rule, though, we do need to rewrite it. So h of x is going to be 1/5 times x to the negative 2. Okay, now let's go ahead and take the derivative. H prime of x is going to be equals to 1/5 times the derivative with respect to x of x to the negative 2. And there we go. Now the power rule comes into play. And we're going to get here a 1/5 times, all right, let's bring down the power, a negative 2 times x. And now we subtract 1 from the power. We're going to get a negative 2 minus 1, which is going to be a negative 3. There we go. We found the derivative here. Now we just need to simplify it a little bit. Our final result is going to be h prime of x is equals to a 1/5 times negative 2 is going to be a negative 2/5 times x to the negative 3, which again, if you want to go ahead and rewrite it with a positive exponent, this is going to give us then a negative 2 over a 5x cubed. And there we go. Now we got the derivative for the h function. All right, perfect. Now, let's go ahead and take a look at another rule here that is very convenient. Now, you may be thinking here that, okay, well, the derivative for a constant was very similar to the limit of a constant times a function. Now, what if we're adding functions and adding or subtracting functions and we wanted to find their derivatives? Well, lucky for us, if we have functions f and g that are both differentiable, then the derivative for a sum or a difference is the sum of the derivative. That is to say that if we're taking the derivative with respect to x of f of x plus or minus g of x, then we just need to take the derivative for f and add or subtract the derivative for g. That is it. All right, so let's go ahead and practice with the following examples. Let's say we're given f of x is equals to 5x cubed minus 7, and we want to find its derivative. All right, so let's see. We're going to get f prime of x is equals to the derivative with respect to x of 5x cubed minus the derivative of 7. All right, now for the derivative of 5x cubed, notice that the 5 is a constant, so we can take it outside of the derivative, and that's just going to give us 5 times the derivative of x cubed minus the derivative of 7. All right, now for the derivative of x cubed, we will be using the power rule, and that's going to give us here a 5 times the derivative of x cubed, bring down the power, that's a 3, times x, raise 1, take away 1 from the power, so it's just going to give us here a 3x squared minus the derivative of 7, oh, that's a constant, and the derivative of constant here is 0. So our final answer then is going to be f prime of x is equals to a 5 times 3, that's a 15, x squared minus 0, which I'm not going to go ahead and write. And there we go. The derivative for 5x cubed minus 7 is just 15x squared. Perfect. Now let's take a look at the other function, which is a little bit more complicated. Because for the second function, we have f of x is equals to 24x minus the square root of x plus 5 over x. Now, notice that we are given radicals and rationals in this problem. So the very first thing that I would recommend you guys to do is to go ahead and rewrite it so you avoid the radicals and the rationals. So once we rewrite, we get f of x is equals to 24x minus x to the 1/2 plus 5x to the negative 1. Now we can go ahead and find the derivative. So our derivative function is going to be equals to f prime is, which is going to be equal to the derivative of 24x minus the derivative of x to the 1/2 plus the derivative of 5 times x to the negative 1. So let's go ahead and take a look here. Now I do notice that I have a couple of constants. So the first term here, we have a 24x. So the derivative is going to be 24 times the derivative of x. Okay, so what can we do to simplify this limit? Because if I let h go to 0, then I would be getting a 0 over 0, and I want to avoid that. So what can we do here? Can we factor anything out? Well, at first glance, it might look like you can factor something out, but I want you guys to remember the rules of exponents that said that whenever we had x raised to the m times x raised to the n, if the bases are the same but the powers are different, we were just adding the powers. Okay, well, why am I bringing this up? Well, notice here that we have on our limit at e raised to the x plus h. So I'm going to go ahead and rewrite this one as an e raised to the x times an e raised to the h. And this is basically just using the rules of exponents. It's just that rather than multiplying two numbers with the same base, this time around we start off with a number that had the same base but had an addition as a power. So we can actually go ahead and split it up as a product. Okay, so with this little background out of the way, let's go ahead and take a look here. So we're finding the limit as h went to 0 for e to the x times e to the h minus e to the x, and it is all over h. Well, now, lo and behold, I actually can factor something out. The first term has an e to the x, and the second term also has an e to the x. So factoring out an e to the x, we're going to be left with f prime of x is equals to the limit as h approaches 0 for e to the x times e to the h minus 1 all over h. Now, notice that for this limit, we're taking the limit as h approaches 0. So what about this e to the x? Is it being affected by the limit? No, x is not changing. It's the h that is changing. So for all intents and purposes, you can think of this e to the x as kind of like a constant. It's not really being affected by the limit. So I'm going to go ahead and take it outside of the limit, and that's going to give us then an e to the x times the limit as h approaches 0 for e to the h minus 1 all over h. Now, this particular limit here, guys, as of right now, there's no algebraic techniques that we can use. So I'm actually going to go ahead and use a numerical approach. And I'm going to ask you to go to your calculator and plug in different values for h, just making them smaller, getting them closer and closer to 0. Or, well, since you're plugging into your calculator, you'll be typing this into your calculator, e to the x minus 1 all over x, and see what happens here as the x gets smaller and smaller. Well, you'll see here that this particular limit is actually approaching a 1. So what is this telling us then? Well, then we'd just be getting an e to the x times a 1, which is just an e to the x. But wait a minute, wasn't e to the x our original function? It was. So it turns out here then, the natural exponential function, it's a very special function. It is a function that is its own derivative. So if we were given f of x is equals to e to the x, the derivative for e to the x is just e to the x. And that's what we have here as our last formula for this particular section at least. If you're given the function e to the x, the derivative of e to the x with respect to x, it is just e to the x. Very nice. Okay, now this was the last rule that we're going to be covering in this section, but I want to give you guys a couple of other problems where it might seem like we cannot find a derivative with the rules that we have so far, but it turns out that if you use algebra first, that can go a long way into helping you figure out a derivative. And that's what I want to do now. So I want to focus here on a couple of examples, but I want you guys to write this down. The theme for this particular examples are, and not just for this ones, but in general, if you can use algebra first and then take derivative. So I'll write it here. Okay, so let's go ahead and begin with problem B here, where we're given the function f of x is equals to x plus 3 times 2x plus 5. Now, as it stands, we don't really know how to handle derivatives of essentially a product. However, we can go ahead and use algebra first and use the distributive property, or FOIL, to get a nice polynomial that we can actually take the derivative of. So let's go ahead and see. Once we go ahead and FOIL, what do we get? Well, we should be getting f of x is equals to 2x squared plus 5x plus 6x plus 15, which we can go ahead and add the like terms to get the 2x squared plus 11x plus 15. All right, so if this one here is our function, now we know how to take the derivative. We've taken derivatives for this before. So the derivative for this one is going to be f prime of x is equals to, bring down the power, 2 times 2 is going to be a 4, x raised to the, take away 1 from the power, so it's just x to the first, plus, all right, so we have the constant 11 times the derivative of x, which is just 1, which I guess I'll put it here, plus the derivative of 15, which is 0. So our final answer then is going to be equals to 4x plus 11. And that's it. There we go. We found the derivative for the function x plus 3 times 2x plus 5. Alrighty. Now, let's go ahead and take a look at another problem here. And let's actually do these two here. So we'll begin with c. Alright, so the function c, we have f of x is equals to x squared plus 3x minus 7 all over x. Okay, now once more, at first glance, it might seem like we don't have the tools necessary in order to take this derivative, because we really haven't seen how to take derivatives of quotients. Well, if we go ahead and use algebra first, we can go ahead and simplify this equation here, or this function. Well, I see that on the numerator I have multiple terms, and I'm only dividing by a single term, so I'm going to go ahead and divide everything on my numerator by the denominator here. So we're going to have an x squared over x plus a 3x over x minus a 7 over x, which is going to give us a new function, x plus 3 minus 7x to the negative 1. Now, you could have also let the function as x plus 3 minus 7 over x. However, since we will be finding the derivative and I want to use the power rule, I brought the x in the denominator here to the top. Okay, so with this new function, what is the derivative? Well, let's see. F prime of x is going to be equals to the derivative of x, which is just a 1, plus the derivative of 3, which is a 0, minus the derivative of 7x to the negative 1, which is going to give us, let's see, bring down the negative here. So we'll get a 7 times a negative 1 times x, take away 1 from the power, negative 1 minus 1 is negative 2, and that's it. Our derivative function then is going to be equals to 1 plus 7 over an x squared. Let me scroll up here. There we go. 7 over x squared. Ta-da! We're done. Excellent. Alrighty. Now, let's take a look at the last one here, where we have d, which is a function g of t, equals to e to the t plus t to the e plus 1 over the cube root of t. Alright, so as usual here, I do see a radical. Even worse, it's the denominator, so we will need to rewrite this one here. And then we'll get g of t is equals to e to the t plus t to the e plus t raised to the negative 1/3 power. If you have any questions as to why I got the negative 1/3 power, please talk to me during office hours, remember, and I'm always there to help. Okay, now let's go ahead and take our derivative. So what is the derivative for the g function? Well, let's see. G prime of t is going to be equals to, now for this one, since we are taking the derivative with respect to t, I'll go ahead and include our notation here, d dt of e to the t plus the derivative with respect to t of t raised to the e plus the derivative with respect to t of t raised to the negative 1/3. Okay, so for our first derivative here, we have the derivative of the natural exponential function, and we know that the derivative for the natural exponential function, it's itself. So we're just going to have here an e to the t plus, now careful with the next one here, we have the derivative of t raised to the e. Is this one here a constant or a variable? Well, the t was the variable, so we are dealing with a variable here. It's not a constant function. So then our derivative is going to be, and this is where the power rule comes into play, bring down the power. So we're going to get an e times t raised to the e minus 1 plus, now another power rule problem here, bring down the power. So we're going to get here a negative 1/3 times t raised to the negative 1/3 minus 1. All right, so what will that give us here? Well, let's see, we're going to get g prime of t is equals to e to the t plus e times t raised to the e minus 1 minus 1/3 times t raised to a negative 1/4. Sorry, negative 4/3. And there we go. It's a little bit bigger here. And this one here should be our final answer. All right, now, if you wanted to go ahead and rewrite the t raised to a negative 4/3 with positive exponents or with radicals, that's okay too, but I will take this one here as a final answer as well. You're still getting full points. Alrighty guys, now I think this is a good place to stop our part 2 for our recording. We'll continue on with more examples in part 3. See you there.